Hi. Thank you very much for a brief introduction. First of all, I have to say there are two problems with my talk. First one is I prepared it in Polish. I'll be speaking English, but I was somehow misled by our chairman a few days ago when he actually asked me to deliver this talk. Let me finish. He said that this talk is supposed to be aimed at actually young people coming from high schools. So I said, yep, young people, high schools, probably Polish. But then I see everybody here using actually English. So okay, so I'll be talking in English, and you can read almost the same stuff in Polish. So I'm really sorry for that. I understand. Okay. Now I understand. Okay. It wasn't that clear over the phone, but all right. The second thing is that actually I have to tell you I feel like a classical sheep surrounded by quantum wolves. So this is the second problem with the talk, because this will be completely classical. All right, let's start. I'm theorist still, but we start from an experiment. The experiment is really easy or really complicated, depends who is doing it. This is a cup. It's supposed to be filled with coffee, but it's not anymore. And this is a really easy example, really easy experiment. I have to push this cup to one side, and you can see it moves. So I can write down an equation, and now comes the theory, which actually describes this beautiful experiment. And this is a really easy equation. I actually neglect the gravity because of this table. I can do it. And so this simple equation you all know. I'm pretty sure all young people know this equation, which actually tells me that the dynamics of this cup will be governed by two forces. One is this force that I push, and the second will be friction. Actually, I can even solve this problem completely, analytically, which is a really good thing. But it's not the point of this talk. The point of this talk that this holds really nicely in a macroscopic world, and this is really easy to describe, solve in macroscopic world. But if this cup will not be macroscopic, will be microscopic, so I have a micro cup, then obviously you will be a little bit different. First of all, you will be surrounded by particles. These are not flies. It looks like flies, and these are not flies. We're surrounded by particles, many different particles. Actually, in one mole, there's like 10 to the power of 23, a little bit more of that, of particles, and they all will be hitting my microcap. So actually, I can draw a picture, which is actually my microcap, which is hit constantly by micro hands, and only one of these hands, this is my hand, my micro hand, which is actually different from any other. It's not really much different. Sorry, I'm one too fast. And I still can write down the same equation. Here I assume that the friction is linear in this system, but it doesn't matter. It doesn't matter here. And this is my hand. This is force coming from my hand. But also I have to count all the forces which actually hit my microcap at the instant of time. And when I count all these forces, then I can tell something about the dynamics of this microcap. And so if this is 10 to the power of 23 of say, hits for this microcap, or possible hits, then this equation will be extremely long, and it will be, now you can imagine, impossible to solve. Actually, it's impossible to measure all these particles, at least. So, to be honest, you have to look at every single hand here, this micro hand, as a particle itself. So, actually, to solve this problem, I have to solve for every single hand the same equation. If I have 10 to the power of 23 particles, they have this much equations I have to solve. And actually, this is impossible even for theorists, even here at the University of Silesia. So Now I have to move a little bit from the main topic to show you how this thing is actually treated by theorists. So this is a plant. It's beautiful, and it's actually called beautiful Clarkia. And the whole story of the description of this kind of micro cup hit by the micro hands around goes back to this beautiful plant. This plant was given to Mr. Robert Brown, who was a British botanist in 19th century. Actually, he died in 19th century. And actually, among all this stuff he did as a botanist, he was extremely active, extremely productive scientist. In 27, he actually received this beautiful Clarkia and start to look for the pollens of this plant. He took the pollens of a plant and put in the water and start to look how they look like, how they actually behave in the water. And he noticed that they move, they constantly move, pollens constantly move. Okay, he thought maybe there's some influence of the water, of the surrounding. So he changed water into alcohol. He put the pollen for 6 months in alcohol. He thought pollen will be obviously dead after 6 months in alcohol. I mean, not everybody's dead after 6 months in alcohol, but pollens would be, and they were, and they still were moving. They're still moving. Here in Silesia especially, and pollens actually were dead, but were still moving. He tried many different pollens, many different dust pieces, and all of them were moving, really irregularly. He made really systematic observations of all these small objects, wrote it down, and wrote a paper about irregular movement of some small pieces surrounded by a fluid. Since that time, actually, these movements are known as Brown motion or Brownian motion, and actually, of course, it's because of this guy, Robert Brown. I mean, he was not the only person who did that, but somehow he was really systematic. He actually made a point. For biologists, actually, he's mostly famous by the discovery of a cell. Sorry, nucleus. Thank you. Cell nucleus. But for physicists, these irregular motions are much more important. He was the person actually who moved or shifted the problem of biology into the problem of physics. I mean, this problem was solved in 20th century first of all by Albert Einstein, and actually was a kind of proof of atomistic theory of things. All right. So the idea is that at every single instant of time, in microwatt, the microcup will be surrounded by another microparticles and will be just hit constantly from every other for all the sides, which actually cause to move. The idea is that on average, it will be hit from every single point, and on average, this particle will not move at all. I mean, of course, it will move from here to here, but on average, I mean, if you count every single particle in your mole, in this 10 to the power of 23 particles, on average, they actually don't move, on average. So we can actually use statistical physics to describe this kind of phenomena, and actually, one of the possibilities is a little bit connected with the Newton equation that we already saw, which is actually if we introduce some kind of complementary force, which called psi, and this will tell us that this force is actually a random force which hit or actually influence the particle, influence the movement, and every single time, then this equation will be called Langevin, and actually this Langevin equation. Actually, this idea is due to Paul Langevin, which was actually presented in 2008, so a long time ago, so more than 100 years ago. So then we can think of solution of this equation. So if we think about the average motion of all these particles, then to be honest, the solution is exactly the same as for macroscopic object. So this random force that actually appeared there, as I said, we can treat it as zero force on average for all the particles. So what we have left on average is exactly the same equation with exactly the same solution as for macroscopic objects. All right. Of course, I'm not going to talk about this simple stuff here. We have to introduce something more complicated. All right. This is another story that comes from biology, and this is a kind of motivation that actually drove me into this very interesting but still classical topic. This is microtubule that you can see here, which is a kind of motorway inside a cell. On top of this motorway, there are molecular models or biological models that actually move from one side to another. And that's how the active transport in a biological cell actually takes place. If you want to take a cargo from one part of the cell and transport it to the other part of the cell, you have to use one of those motors. This is actually kinesin. This is one of several different biological motors that actually move cargos inside the cell. This is pretty efficient way of actually in cell transport, and this even this motorways inside cells actually being made exactly in a place when a cell need it. So it's not like there's a motorway and that's it. Like in Poland, there are 3 motorways and that's it. Actually, when they need the motorway from this point to that point, the cell is actually building this within speed of the second. The whole system actually is extremely complex. You can imagine this is huge protein. This motor is huge protein. Actually, the motorway itself is also a huge protein, which actually consists of 2 pieces. It's alpha tubulin and beta tubulin, which is actually combined together, as you can see here. And the shape of it and the fact that they are alternate each other create something that we can actually reconstruct in a pretty easy way as a potential. So this potential actually, which is showed here, is a kind of sawtooth potential, which is almost like a sinus, like you all know, but it's a little bit shifted to one side. This is pretty crucial for transport in a biological cells. But in general, what I want to say is this is periodical potential. I'm not going to go much more into details. I just wanted to show you. There's some more stuff which is unimportant, but what I wanted to show you is this equation. The equation which actually governs the dynamics of this kind of transportation within a cell, or at least we believe it does, is actually very similar to this one that I showed you at the beginning of the talk. At the end, we have the same random force that actually hits a particle constantly from all the sides. This is a friction. This is exactly this potential that you just show. And actually, the microtubule itself is the kind of source of the shape of it. On top of that, I will really make this picture complicated by introducing time-dependent forcing, which actually means that if you take this sinus and start to rock it there and back like this is more or less what I mean. So this sinus goes there and back. It's drawn here. Maybe not that easy to understand the picture, but more or less I show you it goes like that. Pretty easy. On top of that, this is still my finger here, small micro finger, which is a constant force into the system. The question is how to study this kind of system. And it looks easy, or pretty easy, right? It's still classical. It's one-dimensional, or can be one-dimensional. This is one-dimensional. Well, no quantum tunneling, nothing complicated, really easy. So why not try analytical solution? I mean, the point is there is no analytical solution for this problem. We can't even formulate properly the way we would like to even solve this kind of problem. We can formulate in many different ways the same equation, but still there's no way we can even touch it analytically. I mean, the fault is on the math side, so if mathematicians won't do anything with this, then we still can't solve it. If not this, there's another way. We can actually write down equation for evolution of a probability density for this. Whatever that is, this is really ugly, extremely complicated, really difficult to solve. Even numerically, it's difficult to solve. It's really not easy to even formulate in terms of a numerical solution, this problem. And numerical solution itself has problems if we consider really small parameters. Whatever that means, it's not the easiest maybe in this case way, but it's pretty fast. If you would be able to do it, it's pretty fast. Actually, the most straightforward way to solve this equation is actually simulated. So actually, just make a time evolution. Just look at the time evolution. But the point is, we have to still remember that this term here is random. And if we talk about random process, every single time we have to think at the different realization. So it's something which actually connects classical stochastic world or random world with the quantum mechanics, which is also kind of random, which we have to, as Bartek just showed, you have to average. You have to look at averages. He cannot just look at one single realization. It's the same thing here. We have to look at many different realizations of this or time evolution of this equation. We have to run it many, many times. So the point is that the algorithms that we can use to solve these problems are really easy to code. The only problem is a computer or computer power that we actually need to make statistics work. All right, so we need a supercomputer. So a supercomputer, as you can see here, it's a really long story. I mean, these are not the first supercomputers that were shown or sold to the public. These are maybe the most famous, first two at least. This is Cray 1, which was actually sold in '75. And it was sold, this computer is actually a beautiful computer, but it was sold for $8 million when it appears on the market. And it has a power of 160 megaflops. What is flop? Flop is a floating point operation per second. So it has 160 million floating point operations per second. I mean, this hole, whatever you call it, is what, 15 meters long, maybe? So the speed of my voice is around 300 meters per second. So when I say something, when my voice would hit the end of this spot of this hole, that would take what, 15 of 300 will be like 500 of 300, or 500 of 300. So it's like 30, It's like 15 seconds. 15, what? 20 seconds. No, 20 microseconds, right? 50 minutes. No. Actually, the point is that if you have this speed of computer, it can, if you divide it by or multiply by 500s, you can count how many operations it can do. If we compare it to the cell phone that each and every one of you, and also including me, has a cell phone, then Apple iPhone, which was introduced in 2007, has exactly the same, or had exactly the same speed, the same number, more or less, of megaflops, with a small simple machine that can fit into anybody's pocket. Then in '85, 10 years later, there was Cry 2, which was around 2 gigaflops. Giga stands for billion, which is much faster than this one, but it was, it was more or less as fast as iPhone Apple 4. So also not very. I mean, at that time, of course, it was something, right? But nowadays, it's just funny. At the moment, the fastest supercomputer which is produced in the world is Sunway Taihu Light, which is in China. It consists of 10 million central processing units, and has a possibility of 93 petaflops. Peta is 10 to the power of 15. So it more or less is the same as 28,500 of this kind of small computers that I have in my pocket. Or if you take the newer one, which is a 7, Samsung S7 is 3,700 Samsung S7. I mean, the price of one of those two is probably comparable, but this one scales much better. I mean, operations on this could be much better implemented than on Samsung S7. And so if you have Samsung S7, it's pretty much really powerful computer, which you can actually use to solve our equation. Sorry. If we say about supercomputers, we have to tell about the Moore's law, which actually that was something which was postulated in 70s by Moore, that every single 2 years, the number of transistors will be doubled on CPU. Actually, this law holds for 50 years now. I mean, it's not every 2 years, but every 18 months at the moment. But actually, we doubled, and not we, but the engineers are able to double the number of transistors on a single CPU every 18 months. This is not very true anymore, because, of course, if we talk about CPU, that's still fine. But if we talk about any processor unit, that's already gone. I tell you why later on. The second law that has to be somehow told, in the case of supercomputer, is why do we build supercomputer? We do it because we can use many different CPUs, many different processing units to solve exactly the same thing at the same time. So actually we will say lose 1 day of calculations of computer performance. But if you would run it on one CPU, of course we can have, say, output A. If you run it on 10 CPUs, we can have 10 times, more or less 10 times faster, or 10 times more output, so I mean 10 times A. If you run it on 1 million CPUs, we can have 1 million more, the output 1 million times bigger. This is not really true, and this is according to this Amdahl law, also from 70s, which more or less states that if you divide your computer problem into two parts, one part that can be parallelized, can be run at the same time on many CPUs in parallel, this is P, and everything what's left, which means you cannot run parallel on computers, which is 1 minus P. then the speed up, the only possible speed up would be actually limited by the second amount, by this 1 minus p, by the part of your problem, part of your program that cannot run in parallel. This small p over n is absolutely negligible if you have a lot of processors, so you can skip it. No, I said I'm classical sheep. All right. So it means from this law you can see that actually if you can divide your problem into parallel and not parallel and use the parallel very much, why not? I have to skip a few things, but what I can say is the parallelism is not just one-way parallelism. You can parallel your problem. You can make it parallel in many different ways. There are really costly ideas where you can actually build the supercomputers on many different CPUs. There are many different ways to do it, but I just want to mention this one, which is a GPU, which is a graphical processing unit. This, I have to skip all that as my chairman is telling me, but what I want to just say is recently there's a possibility of buying a new beautiful graphic processing unit, which is just graphic card you have, all of you have in your computers. One is it comes from NVIDIA, and there's a new architecture which is called Pascal. One of that is a Pascal that comes this year. At the end of this year will come, and this is a professional one, professional graphic card, which actually has no output for any monitor or anything like that, so you can't use it to play Witcher or any other game. But it can goes up to 4 teraflop per card. This card is small. This is not bigger than any other graphic card. The same technology was applied for GeForce GTX, which is the code name is GP104, and this one you can buy. You can go to Allegro, as you can see, and buy it for 3,370. This is from yesterday, and this is a small power computer. This is extremely powerful computer that actually has 128 cores to use. Each of these cores, or CUDA cores, it has 20 streaming cores. Each of these 20 has 128 small processor units that you can actually use to compute. So it's 20 times 128, you can count, this is a lot. You can also put all these cards, I mean each one is like $800. You can link it together because CUDA, the newest CUDA, the newest technology from NVIDIA, allowed to do it. So you can build for, I don't know, $5,000, you can build extremely fast supercomputer that you can put under your desk and you can use it for very cheaply. You can use it to simulate extremely complicated things, especially things that I did. And the speed up could go, I mean, when you compare to do really fast, but still a single CPU, then can go on to 3,000 times. So pretty cool. There are a lot of details how to do these calculations, but generally what I want to say, this is really easy programming. If you know C, you can definitely code it. If you know Python, you can code it even easier. So this is nothing as complicated as quantum computer to program. This is exactly the same really easy computation, and everything you know about programming in C also applies to the parallel computing on graphic cards. At the end, I just want to come back to this model and show you really funny stuff. I mean, using computers, we found out something which is not really, or from the first point of view, not really straightforward. So we found out that if I push with my micro hand, this micro cup, to the right, or to your left, it actually starts to move back. I mean, start to move to the right. I mean, I push to the left, it goes to the right. I can't do it here because this is a micro cup, but this is actually what this plot shows. I mean, if I apply force to the right, which is actually here, positive force, the velocity, so I mean, you know the velocity, right? The velocity that's supposed to go in the same direction, so velocity of the cup actually goes to the opposite, I mean, becomes negative. So the cup itself, on average, of course, goes to the opposite direction. I mean, this could be found only by the computer. I mean, there's no way to treat it analytically. This is due to computer. There are many different things, but what I want to remember today, that even if you're classical, if you don't touch quantum things, you can still work with the ideas that are 200 years old. You can still find ideas that are not straightforward, that are interesting, and they are still not yet found. Of course, provided you have supercomputer, or at least some kind of micro supercomputer under your table. And the work that I actually didn't present at all was done in collaboration with many different people. Some of them are sitting here, some of them are already gone. I just want to thank you very much for your attention.